Just a friendly reminder, if you're not asking a question, go ahead and put yourself on mute. You can always unmute yourself to ask a question. All right, so today we will be going through, I'll be sharing the data that I compiled that is actually not just our classroom, but also all 3 sections of Biological Anthropology Lab at Ventura College for this semester. So I'll be sharing the data I've compiled, and then we'll be going through 4 examples of how to complete the Hardy-Weinberg equation. So my advice to you is have something out to write with, have a calculator ready. It will be to your benefit to go through these example problems together. There will also be 4 Hardy-Weinberg problems on your exams that will be beneficial not only for this exercise, but also to help prep you for your exam. Do you guys have any questions at all before I begin? You guys are good? Okay, and Professor Lang is also here with us. Many of you may have Professor Lang for your lecture. Professor Lang is going to help me by managing the chat box. So when I'm in share screen mode, I can't always see the chat box. So Professor Lang is going to help me manage the chat box. And if it's a bigger question that we want to discuss in more detail, then she'll let me know so that we can do that. All right, so I'm going to go into share mode now. All right. Is everybody able to see my screen?
Yes, we could see it.
Perfect. All right, so just some basics about the Hardy-Weinberg equation. It is a method that we utilize for studying genetic change in populations. Remember, evolution is essentially changes in allele frequencies from generation to generation. So the Hardy-Weinberg equation is a method that allows us to do that. If a population is in what we call Hardy-Weinberg equilibrium, it means that the allele frequencies at a locus, remember a locus is the location of the gene on the chromosome. If a population is in equilibrium, then those allele frequencies will remain the same from generation to generation. It essentially means that the forces of evolution are not operating upon that feature at that time. So in order for a population to be in Hardy-Weinberg equilibrium, there's some qualifications or qualifiers. It must be an infinitely large population size. There must be random mating, and it means that there's no gene flow, no genetic drift, no natural selection, and no mutation operating on that trait at that time. Some other basics that we need to keep in mind. We obviously need to know the equation itself, and we need to understand what each variable and what each part of the equation represents. So the equation itself is p squared plus 2pq plus q squared equals 1. The p variable is going to represent the frequency of just the dominant allele. Okay, so remember at each locus, at each location on the chromosome, let's say we're talking about tongue rolling, for example. So at the location on the chromosome that determines tongue rolling, each of us have 2 different alleles. So if we're homozygous dominant, we have 2 capital R's. If we are heterozygous, we have 1 capital R and 1 lowercase r. And if we're homozygous recessive, if we're unable to roll our tongue, then we have 2 lowercase r's. So the P is representing the frequency of that dominant allele. So for example, if there's 50 people in a population, if we're looking at just that trait, just tongue rolling, there's actually 100 alleles present because each person will have 2 alleles at the locus that determines tongue rolling. So the P is representing the frequency of the dominant allele. The Q is representing the frequency of the recessive allele. And then the P squared portion of the equation is representing the homozygous dominant genotype. So those that are capital R in this example. The 2pq, the middle part of our equation, is representing the heterozygous genotype. So those individuals that are 1 capital R, 1 lowercase r, the heterozygous genotype. And then the q squared is going to represent the homozygous recessive individuals in the population. And when we're using the Hardy-Weinberg equation, that's where we're going to begin, because if you have the dominant phenotype, then you're not certain if your genotype is homozygous dominant or heterozygous. But if you are the recessive phenotype, at least for these basic Mendelian traits, if you're homozygous recessive, then your phenotype has to be non-tongue rolling in this example. Okay, so that's why we're going to begin there when we're using the Hardy-Weinberg equation. All right, so next I'm going to pull up Microsoft Word document so that we can work through this together. Do you guys have any questions about the basics before I move on to the actual data and equation? You guys are good so far?
Yeah,
okay,
there's no questions popping up.
Perfect. Okay, so the first tasting paper was Thoreau. So for our classroom, well, our 3 sections, we have 55 tasters. So in your document, either if you have it printed out, you can handwrite it, or if you're typing in like me. So for tasters, that's the dominant phenotype. So if you're a taster for this chemical, you're either homozygous dominant or heterozygous. There were 55 tasters, and there were 12 non-tasters. Okay, so those that are non-tasters for this chemical would have to be homozygous recessive, little t, little t. So for tasters, we have 55. For non-tasters, we have 12. All right, so step 1 is going to be to find the values of P and Q. And the way that we're going to do that, we're going to start with the number of homozygous recessive individuals in our classroom, and then divide by the total number of individuals in our classroom. So we're essentially pretending that our classroom population is a breeding population. So we have a hypothetical classroom population. So we're starting with the number of homozygous recessive individuals. So we're going to start with this number 12. So this is going to be our value of Q squared. It's going to be 12, and then we're going to divide by the total in our population. And we have 67 in our total population. So everybody pull up a calculator. Just a basic one is fine. The one on your phone should work just fine, or the one on your computer if you're on a computer. All right, so everyone in your calculators, we're going to do 12 divided by 67. Okay, and then that big long number, just leave that in your calculator screen, because this is the value of Q squared, and what we would like is the value of just Q. So if we want to take this number of this value of Q squared, we need to take the square root of it to find just Q. So on your calculator, it looks like a little check sign with an X underneath it here. So we're going to hit the square root button, and then we get this number here. So once we get that number, that's when we're going to round. So we're going to round to 2 decimal places. So when we're rounding to 2 decimal places, we find the decimal, and we're going to count out 3. So if that third number is 4 and below, then we leave that 2 the same. Hypothetically, if that number was 5 or above, then we would round that up. Okay, but since this number here is below 4, then we're going to leave our value of Q at 0.42. Okay, so we're going to type in here our value of Q, which is 0.42. Okay, and since we know that P plus Q has to equal 1, if we want to find the value of P, then we just invert it. So we're going to take 1 minus the value of Q to find P. So we're just going to plug it in here. 1 minus the value of Q, which is 0.42. And then we're going to type that into our calculator. So we take 1 minus 0.42, which gives us 0.58. Okay, so here this is the value of P. All right, so some of the common errors that are made, sometimes students end up swapping the values of P and Q. So my advice is make it very clear to yourself, clearly label the value of P, clearly label the value of Q. And then step 2, so once we've got that done, step 2, all we have to do is plug in our values of P and Q into our equation. So the equation itself, P squared plus 2PQ plus Q squared equals 1. So P squared is the same as P multiplied by P. So we're going to plug in the value of P, which is 0.58. And we're over here to the 2PQ, so we see another P, so we're going to plug in the value of P. And then we see a Q, so we're going to plug in the value of Q, which is 0.42. And then we see a Q squared. So Q squared is essentially the value of Q multiplied by the value of Q. So we're plugging in our value of Q, which is 0.42. Okay, and the next step, We need our calculators again. So two ways you can do it. You can take 0.58 and just hit the square button like that, and it gives us this number. Or you can also do 0.58 multiplied by 0.58. All right, and we're going to round to 2 decimal places. So we're looking at that third number past the decimal place. Since it's above 5, we're going to round up. So our value here is 0.34. Okay, now this number is a frequency, and it's representing the frequency of the homozygous dominant genotype. If we want to turn that number into a percentage, piece of cake, all we have to do is move the decimal 2 places. So 0.34 becomes 34%. So we now know that 34% of our classroom population is homozygous dominant at the locus that determines whether or not you can taste the row. All right, in the middle part of the equation, so now we're to the 2PQ. So we're just carrying everything down here. So in our calculators, we're going to take 2 multiplied by the value of P, which is 0.58, multiplied by the value of Q, which is 0.42. Okay, so there's our number there, and we're going to round to 2 decimal places. So we look at the third number. Since it's above 5, this is going to become 0.49. Okay, so that's our value for 2PQ. And that's because we know that 2PQ represents the heterozygous members of the population. All right, so 0.49, that's the frequency for the heterozygous genotype. If we want to turn that into a percentage, piece of cake, we just move our decimal 2 places. So 0.49 becomes 49%. So we know that 49% of our classroom population is heterozygous at the locus that determines whether or not you can taste the row. All right, and then last part of our equation, so we're just carrying everything down here. All right, so this is the Q squared portion of the population. So we're taking the value of Q, 0.42, and then we're hitting the square button, and we're getting this number here. So we look at that third number. Since it's 5 or above, we're going to round up. So this becomes 0.18. So we call this number a frequency, and that frequency is the frequency for the homozygous recessive individuals in our population. And then if we want to turn that frequency into a percentage, piece of cake, we just move the decimal 2 places, it becomes 18%. So we know that 18% of our classroom population is homozygous recessive at the locus that determines whether or not you can taste the chemical Thoreau. Okay, and so last part, and I can tell you guys on any Hardy-Weinberg equation or question I give you on an exam, it's always going to equal exactly 1 or exactly 100%. But because we're using actual raw data and we're rounding, sometimes you're going to get 0.99 or 1.01, but it's always going to be very, very close to 1. And if it's an exam question, it will be 1, I promise. So we're going to take 0.34 plus 0.49 plus 0.18, and we're at 1.01. So we are extremely close to 1. Equal 1.01. And then we want to make sure that our percentages are very close to 100%. So 34% plus 49% plus 18% gives us 101. Okay. All right, how are you guys doing so far? Do we have any questions?
Everyone seems to be doing okay so far, Jessica.
Excellent. All right, so don't worry if this seems like a lot. I know it's a lot of steps, but that's why we're going to do 4 of these together to make sure that all the steps make sense. All right, so now we're moving on to sodium benzonate, sodium benzate. So we're going to flip over here so I can see my data. All right, so for our classroom population, we have 45 tasters. So this is, if you're a taster, it's dominant. So if you're a taster, then your genotype is either homozygous dominant or heterozygous. And if you're a non-taster for this chemical, then you must be homozygous recessive. So we have 22 non-tasters. So for sodium benzate, we've got 45 tasters and 22 non-tasters. So going back to our step one, we want to find the values of P and Q. And we need to start with the known quantity, which is the Q squared. Remember, Q squared represents the homozygous recessive individuals in the population. And that's the genotype that we know for certain. We know for certain that we definitely have 22 homozygous recessives in our classroom population. So we're taking that number and we're dividing it by the total. So we have 67 people in our population. So we need our calculators. So we're going to take 22 divided by 67, which gives us that big long number. Okay, so this is another area where sometimes a step is forgotten. So this is not the value of just Q. This big long number here, that's the value of Q squared. If we want to get the value of just Q, then we need to hit the square root button. So that's the button here with the little, looks like a little check sign with a line over it. So you hit your square root button. And then this number, once we round it, will be the value of just Q. Okay, so if we're going to find the value of just Q, we're going to look at that third number. And since that third number is below 4, we're going to leave at 0.57. Okay, so we do know that Q equals 0.57. All right, since we know that P plus Q has to equal 1, then we can simply invert it. We're going to take 1 minus the value of Q to find P. Okay, so here we're going to plug it in. So we're taking 1 minus our value of Q, which is 0.57. We pull up our calculators. 1 minus 0.57 gives us 0.43. Okay. All right, and my advice, always make it really obvious to yourself. What's the value of Q? What's the value of P? So bold it, or if you're handwriting, make a square or a circle around it. Because I've also seen the common error of swapping the values of P and Q. Okay. All right, so we've got our value of P, we've got our value of Q. So the next step is to plug in the values of P and Q into our equation. So the equation itself, P squared plus 2PQ plus Q squared equals 1. So whenever we see a P, we're going to plug in the value of P. So we plug in 0.43. We plug in a 0.43. There's another P here, so we're going to plug in 0.43. And then there's also a Q, so now we're going to plug in the value of Q, which is 0.57. You see another Q, a Q squared, so we're plugging in our value of Q again, 0.57, 0.57. Okay, so now that we have it all set up, and my advice is always set it up like this. So it's a nice neat line down the middle, that way you don't mix up your numbers. We pull up our calculator. So for P squared, we're taking 0.43, which gives us this number. So we're going to round to 2. So we're looking at that third number. Since it's 4 and below, we're going to leave it the same. So our frequency for homozygous dominant is 0.18. So remember, P squared is always representing the homozygous dominant genotype. If we want to turn it into a percentage, piece of cake, we just move our decimal 2 places, 18% homozygous dominant. Okay, so now we know that 18% of our classroom population is homozygous dominant at the locus that codes for whether or not you can taste sodium benzoate. All right, middle part of the equation, the 2PQ. We need our calculators again. So we're just plugging in the numbers to our calculator now. So 2 times 0.43 times 0.57 gives us this number. Remember, we're going to round to 2, so we're looking at that third number. It's definitely below 4, so we're going to leave that 0.49. Okay, so that is our frequency for the heterozygous portion of our population. If we want to turn that into a percentage, piece of cake, we move our decimal 2 places, 49% of our population is heterozygous at the locus that determines whether or not you can taste sodium benzoate. All right, and then last part of the equation, the Q squared. So we're pulling up our calculator. 0.57 squared gives us this number. So we look at the third number, it is 4 and below, so we leave it 0.32. Okay, so that is the frequency for the homozygous recessive individuals in our population. Turn it into a percentage. We just move our decimal 2 places. So 0.32 becomes 32%. Okay, so let's see how close we got to 1. So we're just adding together now 0.18 for homozygous dominant, 0.49 for heterozygotes. Oops. 0.9 plus 0.32 for the homozygous recessive. Sorry, guys, I keep messing up on my calculator. 0.18 plus 0.49 plus 0.32. So we got really close to 1, this time at 0.99. So remember, with some of this raw data, because we're rounding, you're sometimes just going to get very close to 1. But any question on an exam, I promise you, it'll equal exactly 1 or 100%. All right, so let's check our percentages. 18% plus 49% plus 32 gives us 99%. Okay, so for this chemical, we essentially know that 18% of our classroom population is homozygous dominant, 49% of our classroom population is heterozygous, and 32% of our classroom is homozygous recessive. Okay, do you guys have any questions so far?
No, everything's good.
Good. All right, so next example. So the reason we do 4 examples is to make sure that these steps kind of cement in your mind. All right, so for improp, it's actually reversed. If you are a taster, then you are homozygous recessive. And then if you're a non-taster, then you're either homozygous dominant or heterozygous. So let me pull up our data for improp. All right, for improp, we have 44 of us are tasters. So 44 of us are homozygous recessive, and then 23 of us are non-tasters. So for this chemical, if you're a taster, you're homozygous recessive, and if you're a non-taster, then you're either homozygous dominant or heterozygous. All right, so now that we have our data, our first step, we're going to find the values of P and Q. And to do that, we're going to start with our known quantity, which is Q squared. So to find the value of Q squared, the first thing we need to do is take the number of homozygous recessive individuals, so in this case it's 44, and then divide it by the total number of individuals in our classroom, which is 67. Let me pull up our calculator and take 44 divided by 67. Okay, now careful, this is one of those steps where sometimes people forget, because this number here, remember, this is the value of Q squared. So if we want to find the value of just Q, we have to hit that square root button. So we hit our square root button, and it gives us this number here. So this is going to be our number, our value for Q. So we're going to round to 2. So we look out at that third number. It's definitely below 4. So this stays 0.81. Okay. So we leave that 0.81, and that's our value for Q. Okay, and since we know that P plus Q has to equal 1, then we simply invert it. So we're going to take 1 minus the value of Q, which is 0.81, and that's going to give us the value for P. We pull up our calculator. 1 minus 0.81 gives us 0.19. Okay, so 0.19, that's our value for P. Remember, we want to make it really obvious, either bolded, or if you're writing, put a square or a circle around it. We want it really obvious. What's the value of P? What's the value of Q? So we don't end up mixing them up. And then step 2, we're going to plug in our now known values of P and Q into our Hardy-Weinberg equation. So our equation itself, P squared plus 2PQ plus Q squared equals 1. So wherever we see a P, we're going to plug in the value of P. So So we see a P, so we're going to plug in the value 0.19. We see another P, because remember P squared is essentially P, the value of P multiplied by the value of P. And then we go to our middle part, the 2PQ. So we see another P, so we're going to plug in the value of P. We see a Q, so we're going to plug in the value of Q, which is 0.81. And then we see a Q squared. So we're going to plug in our value of Q twice. Okay, and the next part is we're just doing the math. So we're pulling up our calculators. So we're doing the P squared, so 0.19 squared gives us this number. So we're going to round to 2 decimal places. So we look at the third number. Since it is 5 and above, we're going to round this up. So that becomes 0.04. So that is the frequency of the homozygous dominant individuals in our classroom population. Okay, so to turn that into a percentage, piece of cake, we move our decimal 2 places, so that becomes 4%. So we know that 4% of our classroom population is homozygous dominant at the locus, at the location on the chromosome that determines whether or not you can taste NPROP. Okay, now we're going to the middle part, the 2PQ portion of our equation, which is going to represent the heterozygote genotype. So 2 multiplied by 0.19 multiplied by 0.81 gives us this number. Okay, so we're going to round to 2 decimals. So we're looking at the third number past the decimal place. Since it's 5 and above, we're going to make that, we're going to round it up. So we make that 0.31. Okay, so that's going to be our frequency of the heterozygote genotype in our population for this trait. So if we want to turn that into a percentage, piece of cake, we just move our decimal 2 places. 31% of our classroom population is heterozygous at the locus that determines whether or not you can taste NPROP. Okay, and then last part of our equation is the Q squared. So we're taking the value of Q, 0.81, square it. So we look at that third number. Since that third number is 5 and above, we're going to round that up. So that becomes 0.66. That is the frequency of the homozygous recessive individuals in our population. Okay, if we want to turn that number into a percentage, all we got to do is move that decimal 2 places, so that becomes 66%. So we know that 66% of our classroom population is homozygous recessive at the locus that determines whether or not you can taste NPROP. So let's see how close we got to 1. So let's do our frequencies first. So 0.04 plus 0.31 plus 0.66. So we got to 1.01 again. 1. Let's check our percentages. 4% plus 31% plus 66%, 101%. All right, how you guys doing so far?
Good.
You guys doing all right? Okay. All right, so let's go on to our last example. And if you guys are still wanting more examples, I can do more with you, but this is our last example for the activity. So this is the chemical PTC. So let's go back to our data. So let me just check one thing real quick because I can't read my own handwriting. So let me just check one thing real quick. All right, yeah, so for PTC, so we have 49 individuals that are tasters. So 49 of us can taste PTC. So that means that there's 49 of us that are either homozygous dominant or heterozygous at the locus that determines whether or not you can taste PTC. And we have 18 non-tasters. Okay. 49 tasters, 18 non-tasters. So now we're back to the kind of the standard that we were used to with the first two. So if you're a taster, that's the dominant phenotype. And if you're a non-taster, that means you have to be homozygous recessive at that locus. All right, so our first step is we're going to find the values of P and Q. So we're starting with the number of homozygous recessive individuals. So in this case, 18 of us are homozygous recessive. And then we're going to divide that by the total number of individuals in the population, which is 67. All right, so 18 divided by 67. So we pull up our calculator, 18 divided by 67. Okay, now careful. This is the step that oftentimes gets forgotten because that big long number there, that's the value of Q squared, even with the value of just Q. So we need to hit the square root button. So we hit our square root button, and that's going to be our value of just Q once we round it. So to round it to 2, we're looking at that third number. Since it's 5 and above, we're going to round up. So that means our value of Q is 0.52. Okay, and now that we know the value of Q, we can use that to find the value of P. Since we now know that P plus Q equals 1, we can simply invert it. So we're taking 1 minus the value of Q to find P. So we're plugging in the value of Q here, which is 0.52. Pull up our calculator. 1 minus 0.52 gives us 0.48. Okay, so now we know that the value of P is 0.48. And again, my advice, make it really obvious to yourself. If you're typing, bold the values of P and Q, or if you're writing, make a box around them or circle them or star them, make it really obvious the values of P and Q. Make sure you don't flip-flop them. All right, and then step 2, we're going to plug in our now known values of P and Q into the Hardy-Weinberg equation. All right, so our first part is the P squared. So we're going to take our value of P and plug it in twice. Because remember, P squared is the same thing as the value of P multiplied by the value of P. And then the middle part of our equation, the 2PQ. So we see a P, so we're going to plug in the value of P. We see a Q, so we're going to plug in the value of Q. Oops. Okay, and then the last part of our equation is a Q squared. So we're going to take the value of Q, which is 0.52, and plug it in twice. All right, so now that we have it all set up nice and beautifully, next step is just to do the math. So the P squared portion, so value of P is 0.48, and we're going to square it. And then we're going to round that number to 2 decimal places. So we need to look at the third number past the decimal place. It is definitely below 4, so we're going to leave it at 0.23. Okay, so that number there, that's the frequency of the homozygous dominant individuals in our population. Okay, if we want to turn that number into a percentage, piece of cake, we just move the decimal 2 places, and that becomes 23%. So we now know that 23% of our classroom population is homozygous dominant at the locus that determines whether or not you can taste PTC. All right, and then the middle part of our equation, the 2PQ, which is going to give us the frequency for the heterozygotes. So we take 2 multiplied by 0.48 multiplied by 0.52. Okay, which gives us this number. So remember, we need to round it to 2 decimal places. So we're going to look at that third number. It is definitely above 5, so we're going to round up. So this becomes 0.50. Okay, so that is the frequency. 0.50 is the frequency of the heterozygote individuals in our population. We want to turn it into a percentage, piece of cake. We just move our decimal 2 places. 0.50 becomes 50%. So we now know that 50% of our classroom population is heterozygous at the locus that determines whether or not you can taste PTC. All right, and then last part of our equation, the homozygous recessives, the Q squared. So we're going to take the value of Q, 0.52, and square it, which gives us this number. So remember, we need to round to 2. So we're going to look at that third number. It is definitely below 4. So we're going to leave it 0.27. Okay, so that's the frequency of the homozygous recessive individuals in our population. If we want to turn that frequency into a percentage, we just move our decimal 2 places. That becomes 27%. We now know that 27% of our classroom population is homozygous recessive at the locus that determines whether or not you can taste PTC. Let's see if we got to 1 this time. I think maybe we did. So we're going to take 0.23 plus 0.5 plus 0.27. Yay, we got exactly 1 this time. Beautiful. All right, let's check our percentages. So 23% plus 50% plus 27% gives us 100%. Beautiful. Right, so for our classroom, we were actually very close to what we call Hardy-Weinberg equilibrium, especially for this trait. If a population is in Hardy-Weinberg equilibrium, it will look like this. It'll be 25% homozygous dominant, 50% heterozygous, and 25% homozygous recessive. So especially for this trait, for PTC, our classroom population was very close to Hardy-Weinberg equilibrium. So what that says to us as far as how we're studying evolution and evolutionary changes, of course, we would want to ideally study multiple generations. If we were hypothetically a breeding population that was isolated from the rest of the world, all 67 of us, we would want to study multiple generations. But what this says to me right now is that since we're so close to Hardy-Weinberg equilibrium, there must not be evolutionary pressures that are operating on this trait at this time. So essentially it's not an advantage or disadvantage to be able to taste PTC. Same thing with the first 2 we looked at. I mean, we weren't quite as close to equilibrium for Thoreau, but we were pretty close to equilibrium with Thoreau, and we were also pretty close with sodium benzate. So the only one that our data was not very close to equilibrium is the N-prop. So we had definitely a higher percentage of the the tasters. So definitely a higher percentage of the tasters and in comparison to the non-tasters. So what that might say, I mean, of course, we would need more generations of data, but what that might say, if that continues to be the trend for hundreds of generations, we might be able to say that there is some sort of evolutionary advantage. So it provides the individual an advantage and also higher reproductive success. So if this were to continue for many generations, we might be able to say that the ability to taste N-prop provides an evolutionary advantage to the individual and may even enhance their reproductive success. Okay? But again, ideally we'd want to study more generations than just 1. And, obviously our classroom is not really a breeding population. So what do you guys think? You guys want another example, or is this making sense?
I'm getting it so far.
Does anybody want another example? Everybody's good? Okay, so now I'm going to open it up to exam questions. So your exam is going to open up tomorrow morning, and you'll have all the way until Sunday night to finish it. So it's a 50 question